All right, in this section, we're going to look at logarithmic functions. A log function is an inverse of an exponential function. They undo each other. So it's a little bit like a square root and a squared. Okay, if this is log form, then this is the exponential form that goes with it. This little number down below, the b, is called the base. And it is it's written small and kind of down at the bottom. But this b right here is also the base. And it's called the same name because it's the same number. So let me show you how I remember how to rewrite it. So this starts with a log function, and we can see that because there's the word log in it. So when we rewrite it into exponential form, we start with the base, that little number, and that's a 7 here. And then we go to the other side of the equal sign. That other side is the exponent. So we have 7 to the third, and then we go back to get whatever number is inside that log, equals x. And that's exponential function. Let's try it again here. We start with the little number, b. We go to the other side of the equal sign, get the 2, equals, and then we go back and get that number that's in the base, or inside the log, the 25. One more time, we start with the little number that's the base. We go to the other side of the equal sign to get the exponent, then equals the number that's in the log, 26. So that's how we write. We go from log form to exponential form. We want to be able to go the other direction too. So the way we do that is we start by writing log, and then we take that base, the thing that has the exponent, and that's a little number down below. And then we go to the other side of the equal sign to get what goes after the log. And then it equals the exponent. So we read that log base 2 of x equals 5. So let's do this again. We write the word log, and then we see what has the exponent. That's the b here, so that's the little number or letter that's down below. Then we go to the other side to get the number that's after the log, and then that equals the exponent, in this case 3. One more time, we write the word log. The thing that has the exponent here is the e, so that's going to be little and down below. And then we go to the other side to get the 33, and then we write equals, and it equals the exponent. Okay, and we're going to keep practicing that because we need to be able to go back and forth between those two formats. So we'll use that now. We're trying to find what this equals, so we'll say equals x. And then we're going to use our rewriting in exponential form to solve it. So we'll say 10 to the x power equals, and we go back and get this 100. So you might be able to look at that and you say, oh, well, 10 to this power equals 100. If you can't, then let's deal with this 100. 10 to the x equals, and 100 is really 10 times 10, or 10 to the second power. If we can see that this 100 is 10 to the second power, then we know that that x has to equal 2 because the 10s are the same. And that's our answer. Here you might be able to read it just from that. If you recognize that 10 squared is 100, then you know that this x has to be 2. So the answer to log 10 of 100 is 2. Let's look at part B. So here we're going to say again equals x, and we're going to rewrite it in exponential form. So we're going to start with the 5, the base, and that has an exponent of x equals 1 over 125. Now the idea here is that we want to be able to write 125 in some way to be able to compare it to this 5. So let's take 125 over here and let's break it apart. We can divide 125 by 5, and that gives us 25. And then we can break 25 down into 5 times 5. So now we know that 125 is really 5 to the third. So we can rewrite this like that. And that's already closer to what we want, but here on the right, this is in the denominator. We don't want it in the denominator. We want it in the numerator because this side's in the numerator. So that requires you to remember that when you bring a number up from the numerator, it changes the sign of the exponent. So this becomes 5 to the negative 3. And then you can see that x that we're looking for has to be the same as negative 3 because everything else on those two sides match. So we have x equals negative 3, and negative 3 is our final answer. So part C. Again, we'll start by saying this equals x. So we're going to rewrite it. We start with the little number, and the x is the exponent, equals 5. Well, we can't change this 5 like we've done the other times. We have to deal with this 25. So 25 we know is 5 squared. This still equals x. And this is really 5 to the 1. So here we have to remember that when we have exponents, we multiply them. So we get 5 to the 2x equals 5 to the 1. And that means that this exponent, 2x, has to be the same as that 1 because the 5's are the same. So we can write another little equation off to the side. 2x has to equal 1. We can divide both sides by 2, and we get x is equal to 1/2. So 1/2 is our answer. We'll do one more here of this type. So again, we're going to say equals x, and we're going to rewrite it. So we'll start with that 2, go over here, that's our exponent, equals, and then we go back and get that part, 5th root of 2. So we need to remember how to rewrite this 5th root. I'll just copy the left side. So when we have a 5th root of something, it doesn't matter what it is, that can be rewritten as an exponent of 1 over 5. Anytime you have roots, it's a fraction exponent. If we had a 3rd root of something, that would be an exponent of 1 over 3. If we have a square root of something, that's an exponent of 1 over 2. We don't normally write this 2 in the square root. It's just understood that it's there. Okay, so this, back into our problem here, would be 2 to the 1/5 power. And that tells us that x has to be 1/5. And so 1/5 is our answer. There are some basic properties that can help us do things, find logs more quickly without even having to rewrite them. So we'll look at that here. If this base and the number inside the log are the same, the answer is automatically 1. If we're taking a log of a 1, it doesn't matter what the base is, the answer is automatically 0. If the base and the number match again, the answer is whatever, and it has an exponent, the answer is whatever the exponent is. It's a little bit like that cancels out. And then finally, if we have a base and a base that match, the answer, and the log is in the exponent position, the answer is whatever that x is in the exponent position. It's, again, a little bit like that cancels out. So let's practice that now. Here we have a 9 and a 9, so the base and the number match, so the answer is automatically 1. Here we have a 1 in our log. It doesn't matter what the base is, the answer is automatically 0. Here we have a base and a number that match. So it's a little bit like those cancel out, and we're just left with 5. And then here we have a base and a base that match. It's a little bit like those cancel out. We're just left with 9. So now let's look at the graphs for log functions. The graphs for logs cross at 1 on the x-axis. If b is greater than 1, that base, then the graph comes up through that point and over. It's got a vertical asymptote on the x-axis, so it can never cross that or on the y-axis. It can never cross that y-axis. It can't touch that y-axis. If, on the other hand, b is between 0 and 1, it can't ever be negative, the little number down below, then there's still this vertical asymptote, but it comes down and through that 1 instead of going up and over. This is the way we see it most often. Okay, for both, the x values have to be positive, 0 to infinity. The range, the y values, go down for forever and up for forever. So the range is all real numbers. And the vertical asymptote is x equals 0. That's the y-axis. And that's true for both graphs. So again, we can also move these graphs the same way we moved our exponential graphs. So we'll start by penciling in our log graph. This 4 is bigger than 1. So we have our vertical asymptote on the x-axis, on the y-axis. These always cross at 1, and it would go up through 1 and over. But now this minus 5 is inside the parentheses, which tells us that we're going to move that graph right 5. So what was here is going to get moved right 5 and goes here. That vertical asymptote was on 0, it gets moved to 5. So it's like having a wall on the left-hand side of the graph. That wall has to get moved with that graph. So then it will come up through here, and that purple graph is our final graph. Here's another one. We'll start by penciling in the original graph, just the log of 4. It's got a vertical asymptote on the y-axis. It would cross at 1 and go up and over. But now this plus 2 is outside, so it tells us to go move the graph up 2. So this dot that was here is going to get moved up 2, and it goes to here. The vertical line, the asymptote, when it gets moved up 2, stays where it is, because moving a vertical line up and down doesn't change it. So the graph would come up and then through that point and over. So the purple graph here is our final graph. Common logs are logs that have a base of 10. And this is a log that happens the most often. That's what we call it common. And it happens so often that we usually write it without that little 10 down below. We usually just write it as log of x. And this is the log button that you see on the left-hand side of your calculator. All our log properties work for common logs just like they worked for other logs. So here's an example of a problem. The percentage of adult height attained by a boy who is X years old. So again, pay attention to where that letter is, because that's telling you that X represents years old. Can be modeled by this equation, where X represents the boy's age and f of X represents the percentage of his adult height. Approximately what percentage of his adult height has a boy attained at age 10? So this is telling us that we want to know what happens when x is 10. So we're going to use this equation right here. So we find f of 10. We have 29 plus 48.8 log of 10 plus 1. So again, we can type that in just exactly like you see it in your calculator. You just do 29 plus 48.8, and then you've got a log button on your calculator. Notice this is a common log. There's no number written down here, so it means that there's really a base of 10. We don't write that. It will put a parenthesis there for you, so you just need to write 10 plus 1, close your parenthesis, and then hit enter. And you get should get 79.81996. It keeps going. And it says here approximately what percentage, which means it wants us to round. And the 79.8 is really close to 80%, so I would just call it 80%. Okay, so natural logs. Okay, remember that when we see that word natural, we need to think about the natural number, and that's e. So natural logs have a base of e. They occur very often again. So when we have log base e of x, we usually write it as ln of x. We usually use capital letters so that we don't get confused. And I think I always remember it as standing for log natural. It's still a log, so that comes first, but then it's a natural log with a base of e. And you have an ln button on your calculator. And again, all those same properties work for natural logs that work for regular logs. So let's look at one example that has a natural log. When the outside air temperature is anywhere from 72 to 96 degrees Fahrenheit, the temperature in the enclosed vehicle climbs by 43 degrees in the first hour. This function models the temperature increase in degrees Fahrenheit after x minutes. So again, x is our minutes. Find the temperature increase to the nearest degree after 30 minutes. So we're going to find this when x is 30. So we're going to use this function that they give us. We're going to find f of 30 is equal to 13.4 ln of 30 minus 11.6. And I know that there's no parentheses in this problem, but when we replace x, it's a good idea to always put it in parentheses. And that's how your calculator will do it as well. So we'll type this into our calculator, 13.4, and then we'll use the ln button. It will put the first parenthesis there for you. So you just type 30 and then close the parenthesis and then subtract 11.6. And you get 33.976 ... So it says to the nearest degree, which means we want to round 33.9 to 34 degrees. So this is saying that your car, when you close it all up, in half an hour, the temperature raises 34 degrees. And that's our introduction to logs.